I stopped here in the previous video, and now we move on to some of the keys, the key issues while doing reservoir modeling. So we talked about these issues already, right? And they feed directly into this. The question is, how might the decisions you make based on the outputs of a reservoir simulation, for instance, how could that be affected by the physical mechanisms, by whether the physical mechanisms in the reservoir are represented in your simulation model, for instance? Whatever you predict as the rates and you're making a recommendation on the best operating conditions, how is that affected by the resolution of the grids in the domain, for instance? So everything is connected, basically, is the message on this slide, really. Using the model to test the impact of what is poorly known, and that's important. You need to be able to think through the available data you have that you're providing into the simulation model, and now figure out whether that simulation model built based on the data you have provided is good enough to reach useful conclusions about the question you are asking. So if the question you are asking for a simulation study is, so originally it was all oil, of course, water below. Let's say this is water, this is oil. This was your simulation model originally. And the question is, if a gas cap is formed, meaning secondary gas cap, so you deplete the reservoir with a well and the pressure drops low enough and you start forming secondary gas cap, how big will this gas cap be? Will it lead to gas cooling issues that could severely affect production? So that's a valid question. But let's assume part of the input parameters to the simulation model that you don't know is the bubble point pressure. So the bubble point pressure is poorly known. So we just use an estimate from, say, a nearby field. Well, whatever simulation results you get will be haunted by the fact that the bubble point pressure is not well known. And the bubble point pressure is what determines when the gas comes out in solution. So it determines the size of the gas cap. So whatever you're predicting is going to be useless, basically, because the impact of that bubble point pressure, which is not well known, on the objective of the study is very large. I'll say that again. The impact of the bubble point pressure, which is poorly known, on the objective of the study, which is to find out the size of a secondary gas cap, will make that model not very useful. So model calibration, model tuning, history matching, they all mean the same thing. It's as simple as comparing what your model predicts. You're comparing the results from your model to observed historical data, right? So your simulation model may predict that the pressure declines this way, but you have observed production data from a downhole gauge. And the goal is continue to calibrate. So assuming this was where the prediction was at initial conditions, the first time you predicted flowing bottom hole pressure, this is what you got. Then you keep changing the porosity, permeability, and other parameters until your model begins to line up with the observed data. That's called model calibration or history matching. So adjust it until you get the best match you can possibly get. Many times in real life, you will not be able to match all of the observed data for all of the wells exactly. So you just need to get your best match. Get your model to be as close to the data as possible. What if you are never able to get a good match? Most likely, some of the model parameters are very wrong. So you may need to go acquire some data maybe drill more wells, explore, gather more data from those wells, maybe do MDT, get some more fluids, and do some fluid property studies. And sometimes you just need to discard a model and build another one that honors all of the information available. Trade-offs have to be made during model calibration. And again, model calibration is just changing the permeabilities, porosities, and all the other parameters that were fed into the simulation model for all of the cells in the domain. So there are different combinations of model parameters that can give you a good history match like this one. And that's why we say history matching is non-unique. That means everyone in this class can possibly match this observed data, but with different parameters of permeability, porosity in the simulation domain. So you can have multiple realizations that match the observed data. And when this happens, the goal is to be able to pick the one that is most realistic. All right. But very important to note that the fact that you were able to replicate, to match observed data does not mean that your model is an exact representation of the subsurface. History matching is non-unique. Some more modeling concepts. In the past, back in the day, what engineers did was to use these simplistic proxies for your actual reservoir. So fairly sure model sandparks. So they actually have sandparks and they're trying to make it into a proxy that represents what's going on in the subsurface. And obviously these are not accurate models. For a significant period early in the days of petroleum engineering, electric resistivity and capacitance models were used. So they actually have electric circuits, and the capacitors in the model will represent the storage term in your equation. Electric resistivity will represent hydraulic conductivity, which is driven by permeability. And then from the flow of electric currents in the circuit, they are able to predict the flow of fluid in the porous medium. And again, these are old concepts that have been replaced by reservoir simulation. Analytical mathematical models, so analytical or mathematical models, are likely the most common models you guys have encountered in the course of your petroleum engineering program. And these are some of those analytical models. And how do you identify an analytical model? It's usually an equation. And all you need to do is to provide input parameters and to substitute the values for those parameters in the equation, and you have your objective, whatever you're trying to calculate, very simply. So Darcy's law, for instance, is Q equals KA over mu grad P, which is the PdL, where L is the direction of, is the distance between, the direction of flow. So this is an analytical model. Why? Provide Ka, the PdL, and mu, this dP, you can make it into delta. So difference in pressure between 2 points, right? And the length in between them, right? Provide this and you get Q. Those are analytical models. So anytime you have an equation, a mathematical expression, that is an analytical model. Numerical models, you will need to solve systems of equations for all of the grid blocks in the domain. And so these are some of the analytical equations you guys have encountered. Material balance, which are tank models. We use it for gas, for oil. Darcy's law, which I just gave you here. Diffusivity equation, which you will see shortly. And that's what we use in well test analysis, right? Pressure transient analysis. The solution to the diffusivity equation under certain conditions gives you the different analytical equations we use under steady state flow assumption, under pseudo steady state assumption, under transient assumption, and whether there is water influx. Buckley-Leverett model, you're injecting water into an oil-filled rock and you have this solution, right? Equilibrium solution, not saturation, is a shock front. It's an analytical, there is an analytical solution to that problem. Archie's law in formation evaluation is a mathematical expression. It's an analytical model. The drilling hydraulics equations, analytical equations. And I'll discuss the remaining slides in the next video.